Hello everybody, my name is Thaddeus Foster. I am a student at C&M, and today I'm doing a video presentation on the atomic force microscope, or broken down simply as AFM. In today's high-tech world, everyday tools and products are becoming smaller and smaller. As the reality of cost efficiency and environmental awareness grows, companies are bringing consumers useful devices in micro and nano scales. But like any macro-sized producer, these micro and nano-sized producing companies use tools to measure the output of their products, the input of their materials, and the processes in which they produce these devices. Because of the demand to create these micro and nano-sized products and devices, metrology, the science of measurement, has had to keep up. One tool developed to help measure the input, output, and process improvements is the atomic force microscope, or the AFM. This is a modern tabletop AFM. You could see the imaging monitor to the left of it. This is a stepper, which has basically a stage, a piezoelectric stage, and the cantilever is kind of looks like a little square box on top of a cylinder there in between the microscope lens. That inside that box is where the cantilever and the probe actually exist. The stage itself moves in this in particular image right here. But we're going to move on to our next slide, which should be this one right here. The AFM is a useful tool for direct measurement of microstructures and parameters. The AFM can reveal the intermolecular forces of these structures at a nanoscale level, producing atomic resolution and characterization images. The basic principle of an AFM consists of a sharp probe at the end of a cantilever used to scan the specimen surface. The specimen sample is placed on a stage made of piezoelectric material that expands and contracts proportionally to an applied voltage. When the probe comes within proximity of the sample surface, certain forces, depending on the situation, and those cause a deflection of the cantilever. And depending on that situation, those forces could be mechanical, contact, van der Waals, capillary, chemical bonding, and or electrostatic forces. The deflection is typically measured by the reflection of a laser beam pointed at the top surface of the cantilever, which is received via photodiodes. The frequency in which the diodes receive the reflection tells the detector how to send feedback information to an imaging monitor. In general, the AFM can operate under three different imaging modes: contact or static mode, non-contact mode, or tapping mode. The AFM can be used to image and manipulate atoms and structures on a variety of surfaces by sensing individual atoms on the surface. The tip of the probe forms an incipient chemical bond with each atom that subtly alters the cantilever's vibration frequency. This allows different atoms to be distinguished as well as mapped. So you can see in this image here the piezoelectric scanner down on the bottom there with the sample surface on top of it. Depending on which company you buy your AFM from, either your cantilever arm is going to move back and forth, or your scanner is going to move back and forth. And in either case, the laser bounces off that cantilever as it deflects and bends as it's going over the surface, and it's directed to a photodiode, and that photodiode either sends electrical feedback back through, telling the scanner or the cantilever arm to move either up or down, and also sends into certain apps onto the computer that it's attached to, producing actual images. So on our next slide here, I'm going to give you guys a little history. This is the first atomic force microscope ever produced. Quite a contrast compared to today's AFMs, basically like this image or in this image. But this was, like I said, the first AFM created. It was created by Gerd Beining, Calvin Quate, and Christopher Gerber in 1986. It was developed in an attempt to image non-conducting samples with atomic resolution. Actually, 4 years prior to this, Beining, along with a couple other gentlemen, Rohrer and Weibel, I believe is what their names were, actually invented the STM, which is a scanning tunneling microscope that was used for imaging conducting samples. And the basic difference between the two is obviously one's imaging conducting, the other is imaging non-conducting, but the STM also uses a flat tip probe and not a sharp pointed probe. And also on the STM, the cantilever or the arm is swinging, and it's a swinging arm. It's not a cantilever. I should correct myself there. And that probe swinging across the atoms is what gives you an image, whereas the cantilever is based on deflection and so on, and the different modes in which it can scan. In 1986, actually, Beining and Rohrer won a Nobel Prize in physics for the AFM, and the STM and the AFM are now the foundations on which a wide range of scanning probe microscopy techniques are built. So I'm going to get a little more into detail about how the AFM works. Today, most AFMs use a laser beam deflection system introduced by Mayer and Armour, where a laser is reflected from the back of the reflective AFM cantilever and onto a position-sensitive detector. Angular displacement of the cantilever results in one photodiode collecting more light than the other photodiode, producing an output signal which is proportional to the deflection of the cantilever. It detects cantilever deflections. A long beam path amplifies changes in beam angle. Because the AFM relies on the forces between the tip and the sample, knowing these forces is important for proper imaging. The force is not measured directly, but calculated by measuring the deflection of the lever and knowing the stiffness of the cantilever. So Hooke's law gives us F equals minus kz, or negative kz I should say, where F is the force, K is the stiffness of the lever, and Z is the distance of the that the lever is bent. There is also three standard, let me pull up the first, there we go, contact mode. Basically, there are three standard modes in which these measurements are pulled from. In contact mode, the tip is dragged across the surface of the sample and the contours of the surface are measured, either using the deflection of the cantilever directly or sometimes using the feedback signal required to keep the cantilever at a constant position. Our next one is our tapping mode. I'll give you a little diagram of that as well. If I can find where I left off. In the tapping mode, the cantilever is driven to oscillate up and down at near its resonant frequency by a small piezoelectric element mounted in the AFM tip holder. Similar to the non-contact mode, but not quite the same. The amplitude of this oscillation is typically 100 to 200 nanometers. The interaction of forces acting on the cantilever when the tip comes close to the surface, causing the amplitude of the oscillation to decrease as the tip gets closer to the sample in non-contact mode. In non-contact mode, and we will show you an image for that, the tip of the cantilever does not contact the sample surface at all. The cantilever is instead oscillated at either its resonant frequency, which is the frequency modulation, or just above amplitude modulation, where the amplitude of the oscillation is typically a few nanometers, about less than 10 nanometers, down to a few picometers actually. Our next slide here is some close-ups of actually the probes and the tips of the scanning electron, or the atomic force microscope. A typical tip radius is from a few to tens of nanometers. AFM tips and cantilevers are microfabricated from silicon and silicon nitride. Cantilevers range in sizes, but are typically about 100 micrometers in length and 20 micrometers wide by about a half a micrometer thick. The first atomic force microscope is actually a diamond tip glued to a gold-filmed cantilever. Pretty expensive stuff there. Some of the images that these things can produce on these scales are phenomenal. This is just an example of different types of images that you can get. And basically, you can get them in three-dimensional, two-dimensional. They can show the electrical properties. Just a lot of good imaging associated with these. This image right here is actually, I thought, was really cool. It's an image of an ion sputtered silicon carbide, and it's about a 1.5 micron scanning area, or is the area that they had scanned. I do believe that the height of it is about 40 nanometers. Next image I thought was really neat. It's about a 12 micron scanned area, and it's actually it's all the different steps off the surface of an emerald, or sorry, a sapphire, which I thought was pretty cool. Basically, AFMs just don't work by cantilever and probe alone, and definitely need support equipment. Most important is probably the piezo scanner, which actually moves the sample to be scanned across a cantilever or probe. A stage is also necessary, as it includes a stepper, motor-driven Z-axis stage. It houses the scanner, cantilever, and probe, and includes a precision XY axis stage as well. A video optical microscope is necessary to capture the image of the sample being scanned. An E-box includes all the electronics required to drive the AFM stage, the Z-stepper motor, the piezo scanner, plus functions to access the electronic boards, imaging monitors, and microscope, and software such as LabVIEW. And you probably need a vibration cabinet as well to operate these things. This image right here kind of doesn't show everything because most of the stuff is tucked into the larger cabinet there, and that's the vibration cabinet. The smaller box to the left is the E-box, so basically all the electronics and connections. And these folks here are using a simple laptop for their imaging. And this is different type of this is what the stage or the stepper is. Basically, this is the combination of all the accessories that you need to go along with that. And that's pretty much it. That's all I've got for you today. I appreciate you taking the time to watch my video. I hope you have a good day.